Okay, in this problem we're going to use Green's theorem to find the area of a region. So the problem says use a line integral and boundary to find the area of the regions. So part A is this region which is bounded by these curves C1 and C2. And this is an application of Green's theorem. Remember that if you have a region R and it's bounded by a curve C, and the region is to the left of C, to the left as you traverse, as you go along C, like in this scenario, then Green's theorem says that the integral, if you have a vector field f, which is mn, say, then the integral of f dot dr over c is the double integral of n sub x minus m sub y over the region R. And one application of Green's theorem is when you have a scenario where you have this curve C and then it's bounding this region R, then you can find the area of R and express it as this line integral, 1/2 times the integral of x dy minus y dx along the curve C. And your x and y are your x of t and y of t along the curve. So to find the area of this region, R, we need to evaluate this line integral. And to evaluate the line integral, we need to parameterize the curve, C. Well, your C, in this case, has two pieces because there's the line, there's this part, which is the horizontal line, and then there's this part, which is the circular region, and it's going around in a loop. So I'm writing C as the union of C1 and C2, where C1 is the line and then C2 is the circular path. So what we have to do to evaluate this line integral is we have to split up the line integral into a line integral along C1, which is this part, and then do the line integral along C2 and then add them. Okay, so we have to do C1 first. So for C1, you have a line, and hopefully you remember how to parameterize a line between 2 points. So if you have a point, say P, and then a point, say Q, then to parameterize the line segment going from P to Q, what you can do is you can take R of T to be, well, if you start at OP, and then you can add T times PQ, right? And then T goes from 0 to 1. And then that will make you start at P and then at Q. So let's do that. So our P is going to be negative root 2 over 2, comma root 2 over 2. And so our R of T is going to be negative root 2 over 2, root 2 over 2, plus T times the difference, which is going to be, so the vector from P to Q in this case is going to be 2 root 2 over 2, so that's root 2, comma 0, right? And T is going from 0 to 1. Okay, because if you take negative root 2 over 2 and then add root 2, then you get root 2 over 2. So this is going to be negative root 2 over 2 plus root 2 t, and then comma root 2 over 2. So our x of t for C1 is going to be that, and your y of t for C1 is going to be that. Okay. So now we can calculate this line integral. So we have to calculate the line integral 1/2 over c1 x dy minus y dx. Well, maybe we should write out the dy and the dx first. So our dx is going to be root 2 dt. And our dy is going to be what? 0, right? It's not going to be root 2 over 2 dt. You have to be super careful about that. If your y of t was root 2 over 2t, then your dy would be root 2 over 2 dt. But in this case, y is a constant, dy dt is 0, so dy is 0. That's our, it's 0 dt. That's how you write it. So then the 1/2 times the integral over c1 of x dy minus y dx is going to be, well, you're going to have 1/2. This x dy is just going to be 0. So what you have left is this negative y. So y is root 2 over 2 dx, which is root 2 dt. Integrated from 0 to 1, because t is going from 0 to 1 here. So now we have to do this integral, and I see that I get some simplification, right? Root 2 over 2 times root 2, that's going to be, so if I multiply these fractions, I get 2 on the top and 2 on the bottom, so I get 2 over 2 is 1, and I have a negative 1. So this is going to be negative 1/2 times the integral from 0 to 1 of 1 dt. I just moved the negative 1/2 out, and then this is just going to be negative 1/2. So that's the line integral over c1. So now we have to do the line integral over c2, and we have a different parameterization. This time we have the unit circle, radius 1. Well, that's easy. Your c2 is just going to be given by x of t equals cosine t, y of t equals sine t. But we have to specify where your t starts and where it ends. So we have to think about what our t, so our t is, it's starting at this point here, and then ending at this point here. So what t will you plug in so that cosine t comma sine t is equal to this point? Root 2 over 2 comma root 2 over 2. So what t makes cosine of t equal to root 2 over 2 and sine t equal root 2 over 2? Pi over 4, right? Pi over 4. So you do need to remember some trigonometry. So t goes from pi over 4 to what? The ending is where? What t will you plug in that makes cosine t sine t equal to this? 3 pi over 4. So t goes from pi over 4 to 3 pi over 4. And now we just do the same thing like before. Your dx is going to be negative sine t dt. Your dy is going to be cosine t dt. And so when you do 1/2 times the integral over c2, x dy is going to be cosine t times cosine t, that's cosine squared t, and then you have a minus sine times negative sine t, so you have a plus sine squared t, all this dt, so you have 1/2 times the integral from pi over 4 to 3 pi over 4, 1 dt. And that's going to be 1/2 times 3 pi over 4 minus pi over 4. And that's going to be, the inside you have 2 pi over 4, that's pi over 2. Pi over 2 times 1/2 is pi over 4. And now we just need to add these up. So we take this, and then we take that, and when we add them up, so I'm running out of space here, so I'll just do it over here. So the integral is 1/2 times the integral of c x dy minus y dx is just going to be negative 1/2 plus pi over 4. That's the answer. Okay, let's do another example. So again, we want to find the region, the area of the region bounded by this curve. Okay, and it turns out that the graph looks like this. And if you plug in -1, let's just make sure that our curve actually starts and ends at the same point, because we want the curve to go around in a perfect loop. So if you plug in -1, your first endpoint, into this guy, you can check that you're going to get 0, 0. Is that right? Yeah, because -1 squared is going to be 1, then you get 1 minus 1 here is 0, so then this first thing is 0, and then the second thing is 0. So you get 0, 0, and then you also get 0, 0 when you plug in t equals 1. So what's going on is it's starting at 0, 0. That's when t is -1, and as t increases, okay, it turns out that you're going counterclockwise until you end up at the same point, the origin, when t is 1. Okay, and then R is the region inside this curve. Okay, so we actually have the R of t, right? We have the x of t and the y of t. So this is your x of t. That's your y of t. So let's just write out the formula. So we're trying to calculate 1/2 times the integral of c x dy minus y dx. And our dy, well, our dx is going, okay. So we have to figure out the derivative of x and t, of x and y. And for calculating the derivative of x, it's helpful to distribute first and then take the derivative. Otherwise, we have to use the product rule. So let's distribute t minus t cubed. So our dx is going to be 1 minus 3t squared dt. And similarly, our y, oh, I might as well just write it out. I mean, it's up there, but okay. And then our dy is going to be -2t dt. So this thing that we're trying to calculate is 1/2 times the integral. T goes from -1 to 1 of x dy. So that's going to be our dy. I have a -2t, so -2t. And then my x is t minus t cubed, that dt. And then I have a minus y, 1 minus t squared, and then a 1 minus 3t squared dt. So I have to calculate this integral. Okay, kind of annoying, but this is like a Calc 1 integral, right? I mean, if you just forget all the stuff about Green's theorem, and then the question was, what's this integral? This is something that you could do relatively easily. What we have to do is we have to simplify this thing on the inside. That's what we have to do first before we integrate. Okay, so we just have to do some algebra. So you get -2t squared plus 2t to the 4th, and then minus, parentheses, 1 minus 3t squared minus t squared. So 1 minus 4t squared plus t squared times 3t squared is 3t to the 4th. And this is going to equal, okay, let's just distribute across the negative sign. Get this, and then now let's combine the like terms. We have -3t to the 4th plus 2t to the 4th, that's -t to the 4th. I see a -2t squared plus 4t squared is 2t squared, so plus 2t squared, and then I have a -1. Okay, that's not so bad. So now we have to integrate this. This integral equals 1/2 times the integral from -1 to 1, -t to the 4th plus 2t squared minus 1 dt. And that's going to equal the integral of -t to the 5th over 5 plus 2/3 t cubed minus t, right, from -1 to 1. So this is 1/2 times, okay, when you plug in 1, you get negative 1/5 plus 2/3 minus 1. And then minus what you get when you plug in negative 1. You get negative 1/5. That's 1/5. Then minus 2/3. And then plus 1. And when you calculate this, you're going to get 1/2 times, so negative 1/5. I have a minus 1/5 here, so I'm distributing the minus across. Negative 1/5 minus 1/5, so I'm just doubling everything. I get negative 2/5, and 2/3 plus 2/3 is 4/3, and then negative 1 minus 1 is minus 2. And now let's just get everything in terms of a common denominator, so over 15, so negative 6 over 15 plus 20 over 15 minus 10 over 15. And then that's going to be 1/2, 30 over 15. I get 14 minus 30 is negative 16 over 15. So, wait, hold on. I should get a positive number, right? Okay, what's going on? Did I do something wrong? Going counterclockwise, yes. Okay. X dy minus y dx, okay. Okay. Yeah, why am I getting a negative answer here? Oh, what's going on is actually when t goes from negative 1 to 1, the curve is traversing the other way. Oh, that's annoying. Okay, so I need to parameterize essentially from 1 to negative 1. So I actually need to do the integral from 1 to negative 1. Right, so you start at t equals 1, and then you decrease t to negative 1. Or one thing you can do is you can calculate the integral when you go clockwise, but then multiply by negative 1. Sorry, I just mixed up the order. But anyway, so this is just the wrong order. This is the wrong way. But when you do it, you get negative 8 over 15. Right? So then when you do it the correct way, you get 8 over 15. So one way to fix this would be to say, I guess you could say that you parameterize from 1 to negative 1. Is that something you can do? Go backwards? I mean, strictly speaking, no, but Without making it too complicated, I guess we could, this, even though this isn't strictly true, I think most people when they teach Calc 3 will just say that you can parameterize from 1 to -1. So we use the parameterization from 1 to -1 to make the curve go counterclockwise. And then when you go from 1 to -1, basically you end up switching. So when you switch the bounds, right, you end up multiplying the integral by -1. So you end up just taking negative this. So I have a negative sign, and then this is going to be plus 8/15, and that's the answer. Okay, so I just wasn't careful about the curve possibly going clockwise. I mean, one way to do it if your curve goes clockwise is just to do the integral when the thing goes clockwise and then multiply the final answer by -1. Okay, thanks.